All right, and I think we're good. Okay, fantastic. All right, beautiful. Hello. Where do I have? Oh, I have some notes that I lost. Where do I have my notes? Okay, well, regardless. All right, and I think we're good. Okay, fantastic. Wait. Sorry. I don't know what I did there. Give me 1 second. Yes, okay, here we are. All right, beautiful. So, hello everyone and welcome. This is the first of our 2023 series of guest lectures in the class GSD-6338, Introduction to Computational Design, here at the Harvard Graduate School of Design. It is a pleasure to be here. I love doing this every year. I love teaching this class, but I also love bringing people who actually do computational design in the real world, who are changing the industry, who are advancing research, and who have like a strong voice and that can also inspire all of us. And in that sense, I'm actually really happy to have Andy, who has kindly accepted my invitation. We're friends for many years, and I will get into that. But before we get into Andy and the lecture, etc., I would like to talk a little bit of infrastructure. So we are conducting this as a pure online lecture. The lecture right now online is conducted over Zoom, and the participants that are on the Zoom call are the students of the class and Andy and myself. However, this lecture is also being right now live streamed live to YouTube, so that other people who are also not part of this class can also participate from this lecture. All right. I can see actually right now in the chat people saying hi and mind blown, etc. There's a lot of activity going on over there. So what we're going to do is that Andy is going to introduce his lecture, and then after he is done, we will have a round of questions that we will start here in the Zoom call, and then I will open those questions to all the people in the chat. People who want to ask questions to Andy are more than welcome to post those questions on the chat, and I will relay those questions to Andy. Okay. I also want to remind people in this call, in this Zoom call, that because this is excuse me, that because this is live streamed to YouTube, if you have issues with your face or your video showing up on YouTube, I recommend that you don't turn on your webcam. Okay. All right. And without further ado, I would like to introduce Andy Payne. Andy Payne is a doctor of design from the Graduate School of Design. That's actually how we met many years ago. He has given lectures everywhere. He has taught in many institutions. He has perhaps been more popular or more well-known in the community of creative computation by his contributions to the Grasshopper community in the form, for example, of being the co-creator of Firefly and also being the co-creator of Monolith, two very popular plugins for the Grasshopper ecosystem. And he's currently software engineer, software architect. You may want to qualify that better for us, at Robert McNeil and Associates, which is the company that creates, maintains, and manufactures Rhino and Grasshopper. All right. So with that, I am very excited to have you here. I have not checked in on what you've been doing for the many years now. So this is also a very exciting moment for me to see what you've been up to. Thanks a lot. And whenever you're ready, the stage is yours.
All right. Thank you, Jose. Let's see. It says I can't, it says that you're sharing your screen, so that I can't share my screen. Sorry.
I can see your screen right now. I was seeing your screen. I was seeing your browser and your desktop with some kind of large moon on it.
That wasn't me, though.
I don't
know who that was.
Oh, okay.
I thought that was you, but maybe we got hijacked. Can you see my screen now?
Yes.
All right, yeah. Perfect. Thank you, Jose. I appreciate the introduction and really the invitation to come back to the GSD and more specifically to this particular class, because I feel like it wasn't all that long ago that I was a student taking this course and getting to learn all the interesting concepts around computational design.
And my TF.
Well, so it's a pleasure to get to come back now and contribute in a slightly different capacity, but thank you for the invitation. I really do appreciate it. As I was preparing this presentation, I started trying to come up with a theme that might encapsulate all of my work, which is a little bit difficult, but I was reminded of a talk that I listened to very early on in my career, which has stuck with me all of these years. And the presenter was my friend and colleague, Andrew Cudless. And he was recalling a time in his life just after he had finished graduate school. I'm sure some of us on this call can relate to the feeling that Andrew was feeling when he recalled just how burnt out he was after graduate school. And he even began questioning what his future in the industry might be. He even went so far as to move to Japan and considered enrolling in a school to become a traditional Japanese carpenter. And while he never really ended up enrolling in the course, one of the interesting things he remembers or he recalls is that during the first year of your apprenticeship, each carpenter spends their entire time building their own set of woodworking tools, which they then use for the rest of their careers. So before a carpenter can even begin learning how to create these highly detailed and intricate joinery patterns or even contributing to a larger scale building project, they first have to spend a year of their time not only becoming familiar with the vast array of tools at their disposal, but also augmenting or adjusting the tools so that they fit their own body and working style. And to me, I found this concept, which I'm calling design tooling for lack of a better word, really fascinating. The idea that a craftsman must learn how to create or at least modify their own set of tools before they can learn how to design or create the object that they want to build was really important. And I believe it's influenced almost all of the work throughout my career. And so I'll just leave it to you guys to see if you can see how this thread weaves its way throughout my work. So to start, I'd like to take us back almost 15 years ago, back to 2008. I had recently finished my graduate degree at Columbia, and I had moved to San Francisco to work at an architecture firm. I think, like many young architects, I was a bit dismayed when I compared the difference between a typical working day in an office compared to what you might do during school. And I think I felt a bit disgruntled because I didn't feel as mentally or creatively challenged during my day job as I had been at school. But instead of letting that discontent fester, I really decided to channel my energy into research projects that I would explore at night and on weekends. And it was during this research period that I came across this interesting phenomenon called nastic responses, where various types of plants would physically move according to different environmental stimulus. Here, you can see a yellow crocus flower, which opens and closes according to changes in thermal fluctuations. What I found interesting is that there's also some man-made materials that behave in a similar way. Take, for example, shape memory alloys, which are a nickel titanium alloy, which can shrink up to about 8% of its length when it's heated up. It acts in opposition of almost every known material, whereas most materials expand when they're heated up. But shape memory alloys display this unique sort of inverted performative quality. And so I set out to design and build something that could take advantage of this. And what I ended up with was an architectural facade panel system that was completely energy independent, yet could open and close to allow for natural ventilation based on changes in thermal variations. As the surrounding temperature increased, the shape memory alloy wires would contract, causing the opposing panels to open up. Then when temperatures cooled back down, the shape memory alloy wires relaxed, allowing the elastic bands connected to each panel to pull them back into their closed position. To test my design, I built a physical prototype. I then used a heat gun to blow hot air into an enclosed chamber. As the hot air rose inside the chamber, it would heat up the shape memory alloy wires, which in turn opened the panel system. You'll notice there are no electrical wires or batteries. It's completely energy independent, relying solely on the natural material characteristics to drive the functional parameters of the facade system. As I applied for a patent for this design, I began to explore different variations on the concept. Because you see, most applications which use higher temperature shape memory alloy wires use electricity to heat the wires up. But by using electricity to trigger the physical contraction of the wire, You could precisely control the opening and closing of the panel system based on any number of stimulus. Using sensors, you could have the panels driven by changes in light, noise, or even the presence of people within a space. But building these physical prototypes was a time-consuming and increasingly expensive endeavor. So I started looking for ways in which I could speed up the design process. And that's when I hit upon the idea of Firefly. You see, Firefly is a Grasshopper plugin which connects physical input-output devices like sensors or actuators and microcontrollers to a digital 3D modeling environment like Rhino and Grasshopper. It was also around this time that I met Jason Kelly Johnson, an architecture professor at the California College of the Arts, who had also been toying around with similar ideas. So the two of us set out to see if we could build a plugin or a new workflow that could bridge this physical and digital domain. Here you can see some simple examples where I'm using a sensor, a light sensor in this case, where I'm covering it up with my finger to drive a digital animation or a digital simulation where the light sensor controls the height field and a button controls the density of the perforations. We could also use input parameters like sliders or Boolean toggles to drive physical actuators. In this case, I have a slider, two sliders that are controlling the rotation of two servos in a pan tilt servo configuration, where you see a digital simulation, but you also get the real world output. But we weren't just interested in the Arduino and the things that connect with that. We also were interested in other types of devices like the sensor on my phone, a microphone, which could wirelessly send a signal over to my computer and simulate a wind vector blowing on a flag. Or in this case, using webcam or computer vision systems like the Microsoft Kinect, which we could then map the positions of our bodies to things that could control like the brightness of an LED or the position of a servo motor. And so these were just a couple of silly little demos to give you a brief glimpse of the types of things that you could do with Firefly. But let's fast forward another year, and it's 2010, and I've just enrolled at the GSD to pursue my doctoral degree. And it's, sorry, I'm getting a little bit of feedback, but it's my first semester at the GSD, and I'm enrolled in a robotic CAD/CAM class at the GSD and cross-enrolled in a class at the MIT Media Lab called How to Make Almost Anything. And being a bit lazy and partially overwhelmed by being back in school after working at an architecture firm for 5 years, I thought I might be able to save some time by creating a single project which would satisfy the requirements for the final project in both of those classes. And the topic I chose to explore was robotic motion control, specifically for architects. Over the last 10 to 15 years or so, we've seen increased usage of robotic manufacturing in architecture projects. And why not? They're incredibly versatile since you can attach various types of end effectors to the end of the robot. And they can be programmed to do many repetitive tasks with an accuracy that would be pretty difficult to replicate by human hands. Yet programming a robot is not an easy task, right? It typically requires a great deal of training and domain expertise to do it correctly, which is why it's often done by a consultant. But if the consultant finds some sort of errors during the programming process, such as collision detection errors or reachability issues, then the design must be sent back to the architect and the process has to be started again. And what I wanted to do was create an intuitive interface for architects to be able to control a robot. Something as intuitive as one of the many drawing tools, for example, that architects have historically used to help them draw or design their own buildings. And so I set out to design and build a tangible controller that followed the same joint and axis configuration of the ABB IRB 140 robot that we had access to at the GSD at the time. Incidentally, I'd love to know if that's still in use. But anyway, since I was part of this class called How to Make Almost Anything, all of the parts of the design had to be built by me. So here you can see the final design complete with water jet cut aluminum parts, high precision potentiometers to track the angle of rotation around each joint, and custom circuitry which will allow a user to start and stop the recording of a given sequence of movements. And as I said, as part of the final requirements, we had to build every aspect of the design. So I also had to build and program my own custom circuit board. And here you can see what is essentially the equivalent of a custom-made Arduino Uno. The microcontroller was programmed to read all of the sensors mounted to the controller and stream it to Grasshopper via Firefly to perform a digital simulation. So here you can see a as I move the tangible controller, the sensor data is fed into the computer, and I perform a forward kinematic solver to determine where the endpoint of the robot is. Once I know where the endpoint is, I can start to track that over time, and each point is recorded as part of the rapid code, which can be saved out and sent to the robot and replayed. But we took that a step further because I also wanted to be able to stream the live information directly to the robot. So you get a one-to-one interaction between moving the tangible controller and watching not only the digital simulation, but also the real world robot moving in the exact same way. So the result of the project culminated in me essentially attaching a pin to the end of the robot and having it mimic my movements as I wrote my name, which wasn't necessarily all that overwhelming. But I think the real success of the project came in the invention of a new workflow, which enabled architects greater accessibility and control over the robotic manufacturing process. All right, so let's fast forward again another year. And I'm in my second year now of my doctoral degree. It's probably 2011, and I had just taught a workshop which was sponsored by Objet. Objet was a 3D printing company, which was later acquired by Stratasys, which had developed some amazingly sophisticated hardware capable of depositing various types of resins throughout the volume of a 3D printed part. The resins used during the printing process could be combined to make vast arrays of material properties. The materials range from soft rubbers to hard plastics, clear materials to opaque materials, which could also contain any number of colors. Essentially, all of the material characteristics could be dialed in to enhance the aesthetic or performative quality of the 3D printed parts. So after I taught the workshop, a member of the Objet team reached out to me to see if I would write a few posts for their blog. And in exchange, they would offer some free 3D printing services to explore the technology. Now, my dissertation topic was not really focused on additive manufacturing. And unfortunately, I don't really have time here to be able to present that body of work. And who knows, maybe, Jose, we can schedule a follow-up where I talk about that in more detail. But I decided that if I was going to generate enough content to write about it on their blog, that I really needed some help. And so I reached out to a professor of mine at the GSD named Panagiotis Michelatos to see if he would be interested in collaborating on some of this research. And what we found pretty early on is that the hardware had surpassed the software in terms of full volumetric control of material distributions. You see, almost all of the design software that we were used to using use what's called a boundary representation, or BREP for short, to define the geometric form of an object. In a boundary representation, we're usually concerned with the outer surface of the object we're designing. Everything on the interior of the object is treated as a solid, homogeneous piece of material. And historically, there are good reasons why this type of representation was adopted by, let's say, 99% of all the design software makers. I mean, early on, computers weren't nearly as powerful as they are today, and we needed an efficient way to define geometric objects. Boundary representations allowed for sparse geometric definitions and was easy on the designer, who was mostly concerned with the formal aspects of their designs. Yet, as the hardware has now become more sophisticated and we have ways to be able to manufacture parts whose material properties vary throughout its volume, we needed to rethink the underlying geometric representation we were using to define these objects. And what we settled on was something called a voxel representation. A voxel is just short for a volumetric pixel. In a voxel representation, we store a three-dimensional grid of cells where each cell can contain information about that location within the volume. Pixels, for example, contain channels, red, green, and blue, which describe the overall color of a point in a two-dimensional plane. For our voxel representation, we decided to create two channels, which would define a 3D object. The shape channel defined the solid void relationship of the part. We used a level set operation to determine the surface boundary between the interior or exterior of the overall shape. And the material ratio channel used grayscale values to determine the blending of two materials. Full black would represent 100% of one material, and full white would be 100% of the other material. Any grayscale value in between would represent a mixture of these two materials. Combining these two channels enabled us to define very precise volumetric distributions of material, specifically for multi-material 3D printing. So we set out to build a desktop application, which we called Monolith, which would allow us to describe these two different voxel channels to create 3D objects. And the following is a series of clips which sort of highlight some of the ways you could work with these voxel fields. For example, we had some methods which would allow you to sort of paint within a 3D volume. Here you can see I'm painting in the shape channel, and it's using a signed distance field to sort of offset from the brush stroke. But depending on which channel you're doing, you could either draw in the shape channel or the material ratio channel to alter the overall desired effect. We could also create implicit surfaces using formulas, in this case, like a gyroid surface, by creating a series of equations which would control either the overall shape or the material ratio within the volume. We could also blend between, use images to loft a form together. The same way you would loft two shapes together, let's say in Rhinos, two curves, you could, in this case, we're using 2D images to create that lofted shape. Or we could extrude them in orthographic directions. Here we have some images that we're extruding in the XY, the YZ, or the ZX axis. And it allows you to create really interesting forms very quickly by blending between these two different shapes. As I mentioned, one of the benefits of voxel-based modeling is that unlike boundary representations, it lets us to actually control the deposition of material within a volume. So here you can see I'm actually painting on the interior of the Stanford Bunny. We could use things like geometric objects like points and curves and lines and so forth to create signed distance fields. So basically measuring the distance from that geometric object. And depending if we're in the shape or the material ratio, we can actually control the blending between those two different fields. We also had a tool which let us sort of sculpt in a way where you could actually push and pull on points to create a sort of weight on that point. And that weight would then control the overall shape of the object that you were working on, or control the field, the voxel field that you were working with, whether it was a shape or the material ratio channel. So there were a lot of different ways, or a lot of techniques that we began exploring to how we could work with these different voxel fields. But we also created a Grasshopper plugin for Monolith. In this case, one of the benefits of voxel-based modeling is that it can do Boolean operations very quickly. So here, depending on the strength, whether it's positive or negative, you're essentially performing Boolean operations on the voxel field, which would allow you to create really intricate Boolean operations. We could take stacks of images, right? Since it's very close to a three-dimensional grid of pixels, we could create stacks of images. In this case, I'm using an MRI scan of my own brain to create a 3D reconstruction, just like in other MRI technologies. One of the limitations in Rhino and most CAD software is that it's mesh-based. And so meshes, you can't really look inside of the volume, inside the mesh. So we actually created a special component that would allow us to visualize the volume. We could also discretize a gradient and into unique steps, and then output the mesh of each of those steps to be 3D printed separately. Or, as I mentioned, you could create these signed distance fields to create unique shapes and then export that as a volume file, which could then be opened up within the main Monolith application and have further editing. So those were a bunch of techniques that we used to explore how to create different fields, whether that was the shape or the material ratio channel. But we also wanted to provide some tools which gave the user greater control over how the gradient between two materials were combined within the part. We could use a dithering pattern to create a smooth, continuous gradient, but we also wanted to provide other opportunities to apply, say, a 2D pattern or even a 3D pattern to the gradient distribution, where the density of those patterns are varied such that the overall gradient effect was still maintained. So there are obviously a lot of different ways you could apply these patterns. Here, what's unique here is that we're actually using not just a UV mapping, but a UVW mapping, where W is going on into the interior of the object. And so we're applying different patterns in different ways, which again, right now we're simulating using color, but you have to remember that some of these parts you could be printed with hard plastics and soft rubbers. So you could also be generating unique effects that way. Here, you can create your own pattern. I'm creating a two-dimensional pattern of a cross or a grid, if you will. And then I can save that out as an image, which then can be applied to the material gradient. So I'm using a gyroid with a vertical gradient, but here I'm using the cross to create, and depending on how I want to do the mapping, I can actually create really intricate grid patterns within the volume that still simulates the overall gradient effect. Or I don't have to just use 2D patterns. I can use the model itself. Here I have a gyroid, a periodic gyroid that I'm using. I'm using that as the pattern that is now propagated on the interior, sort of at a mesoscopic scale to simulate that gradient. And so there was a lot of unique capabilities. For example, this allowed us to create things like this, where we were able to control the artificial grain, where I'm using a black soft rubber and a white hard plastic. And depending on the pattern that is applied, we can then begin to control the bending or the areas of stiffness and how things bend on a part. Or we can apply patterns such that we get view-dependent occlusions, right? So depending on how you're looking through a part, it controls what you can see and what you cannot see. Now, another benefit of using a voxel representation is that there are a number of algorithms that currently exist simulations algorithms that build upon voxel representations. And one of these is called topology optimization. And topology optimization is simply a form finding process which tries to find the optimal shape given a load condition. So we were also able to build in a structural analysis solver, a topology optimization solver, where here I have a load on the top and 2 point supports. And then I perform this structural simulation to find the optimal shape that we could use to support a given load of that type. And we're able to visualize it in different ways, or even extract both the principal and the major and minor principal curvature, which we could export as curves over to Rhino and then pipe or 3D print or visualize in some other way. So there were a lot of interesting avenues to explore using structural optimization. Here, we're able to create some unique parts. At the top of the slide is a grayscale image of the optimized density distribution for a load case where a continuous load is on top and we have 2 fixed supports on either end. And the form finding process reveals a structural solution which mimics that of a truss, which makes sense. But we were able to use multi-material 3D printing technology to print these parts using a clear rubbery material and an opaque hard material, creating a sort of bone-like, quasi-bone-like structure. And at the bottom, we wanted to create a part using the same grayscale density distribution, but we were using metal printing technologies where we're limited to using only a single material. However, by applying a periodic mesoscopic pattern, like I showed before, we could simulate a gradient where denser areas become more solid and areas which require less support become more porous. And using topology optimization gave us the ability to create some forms that would be incredibly difficult to model using traditional digital modeling techniques. Take, for example, a load case that mimics that of a leaf. And that's to say, we have a cantilever load on one end and a point-to-point support on the other. And the structural form that emerges from the topology optimization process is a sort of venation pattern, which mimics the structures found in nature. Again, this part was printed using a gradient between clear rubber and opaque hard plastic, depending on the structural density requirements. Now, Monolith was acquired by Autodesk back in 2015, and both Panagiotis and myself continued to work on the project for several years. Yet, sadly, the project was shelved back in 2017 and unfortunately is no longer publicly available. Still, I learned a lot from this project, and there are parts of this that still manifested in later projects that I've worked on. All right, so let's fast forward again a couple of years now. In fact, let's fast forward to 2 years ago this month when I joined Robert McNeil and Associates to work on parts of the Rhino and Grasshopper projects. And one of the first projects that I worked on, and one that I now lead, is one called Rhino Compute. Now, if you're unfamiliar with this project, the basic definition is that it's a web server that can perform geometric calculations using Rhino's geometry library. And that might just look like a jumble of words and jargon on a screen. So let's break it down a bit. First, it's important to recognize that it's a web server. That means you can communicate with it using traditional HTTP and HTTPS protocols. Secondly, Rhino Compute is just one example of using what we call Rhino Inside. Rhino Inside is basically an open source project which allows Rhino and Grasshopper to run inside other 64-bit Windows applications like Revit and AutoCAD. But with Rhino Compute, there's no graphical user interface, so you can't really interact with it in a traditional sense. However, you can send it still HTTP requests and have it solve a Grasshopper definition or perform some other Rhino calculation. And you just have to communicate with it over these REST or HTTP protocols. So we have examples for Rhino Compute where you can essentially any client that is capable of sending a standard web request can be used with Rhino Compute. And we have these examples for .NET and Python and JavaScript, which can be looked at and reviewed. We also, the other reasons why you might consider looking at Rhino Compute in your projects is that it gives you access to Rhino's API outside of Rhino and or Grasshopper, right? You don't have to have a working instance of Rhino and Grasshopper open and working on your screen, but you can still call the API. It also allows you to have a single location, store documents in a single location, allowing for more efficient collaboration amongst your teams. And you can solve these documents or functions or whatever you want to call it in parallel, which is also has the potential of speeding up large projects. Lastly, it lets you run asynchronously, so long calculations won't necessarily block the Grasshopper interface. And so there's a number of ways you can interact with Rhino Compute, but the way we typically suggest to users is to start with a plugin called Hops, which you can download via the Rhino package manager. And once you install Hops, it will automatically start an instance of Rhino Compute in your taskbar every time that you launch Grasshopper. And what Rhino Compute and Hops lets you do is essentially Hops becomes the client which sends definitions over to Rhino Compute to solve them. So it lets you take something like this, which in many cases we would call this spaghetti code, and encapsulate it into a function which is then solved on Rhino Compute and returns the geometry. So it encapsulates it into a much smaller, much more readable package and cleans up your spaghetti code. And the way it's able to do this is that it has a certain number of types of components that you use, which will define the inputs and outputs of the Hops component. These are called context get components because they kind of change depending on where they're being used. But in this case, we have a number of components that let you define inputs. And we also have a number of components that let you define outputs. And then the middle, we have the body of the function, which can be, we use standard Grasshopper components and really most third-party plugins to translate these input parameters into output values. So once you have the file or the function that you want to do, in this case, I'm adding two numbers together to get a result, you can tell Hops to go find that Grasshopper file, and it will then serialize that file and send it over to Rhino Compute. And Rhino Compute will interrogate the file and send back a response, which tells the component how to build out the inputs and outputs. Meaning by default, there are no inputs and outputs until you get that response. Now it knows after it fed that definition using the context get components that I have two inputs called A and B and an output called R. Then once we assign it two values, it sends a second request over to Rhino Compute, which will then perform the calculation using those two values and give you the end result. So Hops is a really simple way to get started using Rhino Compute by building out these functions. But once you have these functions defined, here you can see it's a very simple example where we're creating, say, a metaball table, if you will. You can take that same example and make a request to solve this using a web interface. So here we have a web interface that's performing, that is sending a request each time a slider is moved on the screen. And that makes a call to Rhino Compute, which sends back the geometry that's needed to be visualized in the web interface. So there's some really wide-ranging applications that this could be applied to. We also have a new version of iRhino that is being developed internally from scratch. But one of the things we've been exploring is that you could also send web requests from iRhino, for example, to, in this case, I'm looking at a grasshopper definition, which has a few parameters like length and spacing and the number of ribs and so, those sorts of things. But instead of solving this on the iPad, we can actually send a request with those input values and let Rhino Compute do the calculation and then send back the geometry, which is visualized in iRhino. So there's a lot of potential, I think, that can be explored using Rhino Compute. A second project that I've had the opportunity to work on since I joined McNeil is the further development of Grasshopper for Rhino 8, for example. And you're probably asking yourself, why does Grasshopper even need further development? It seems to have probably hundreds of components and maybe even hundreds of third-party plugin developers who develop components for it, which really give it almost all the functionality that could be required. But as you start to use Grasshopper, you may notice that there are still a few gaps in what it can do, right? For example, Grasshopper really has no idea the concept of a Rhino layer, for example, or for that matter, a Rhino material or annotations, right? There are some basic, in Rhino 7, there are some basic annotation components, but they don't really use the native annotation objects that are native to Rhino. And similarly for blocks, there really has been no ability to create or manipulate blocks. And so there are these gaps that exist in the current component set that we really wanted to address in Rhino 8. And so at Rhino 8 beta, which is now available, if you have a Rhino 7 license, you can download Rhino 8 beta for free and try it out. But Grasshopper for Rhino 8 now has at least over 100 new components to sort of fill in some of these gaps. And these are just some of the examples. So I'm going to talk a little bit about how these components work. And to do that, I need to first explain how the components work, right? Traditionally, Grasshopper has used this constructor deconstructor way, right, to handle data types, right? For example, if we wanted to construct a point, we have 3 input values and the output is a point, which is defined here in the case 2, 4, and 6 coordinates. If we wanted to deconstruct that, meaning we wanted to get access to the X, Y, Z coordinates, we have a second component that achieves that. The problem with this is that we have 2 separate components, which then makes the ribbon list of all the number of components double, right? When we really have the ability to combine these into a single component, which we're calling a pass-through component. And I want to explain this a little, how this works. The pass-through component still has the ability to construct a point, right? It has 3 input values, and the output is still a point here, 2, 4, and 6. Or we could take in a point and we could still extract the attributes, in this case, the X, Y, and Z coordinate. If you also assign a new value, let's say for the Y coordinate, it's still creating a new point and keeping all the existing values, but only changing the one input parameter that has changed. And so we didn't want to, that's basically how these point components work. With these components, the very first input and output parameter is always going to sort of contain the main data type, in this case, a point, right? And then everything underneath it is the attributes that define that data type, right? And so we didn't, and this is just one example. We didn't, since the point component, constructor and deconstructor typology has been around for a very, very long time, over a decade at least, we didn't want to reinvent all of the components that currently exist and thus change your existing definitions. So all of the existing components like this are still the same, but all of the new components that we've been developing all use this new pass-through idea or concept. So the point doesn't really exist, but we do have a new component called a model layer, for example. And the layer, as you can see, the top is the main data type and the bottom are the attributes. And you're probably asking yourself, what are the attributes? Well, the attributes of any data type are really just the parameters that define that specific data type. If you look at the layers panel in Rhino, you can see that a layer is defined by its name, its display color, its line type, its material, things like that, its visibility. So all of those attributes are now exposed within this new model layer component. So let's look at a quick example. Let's say we wanted to create a new layer called geometry layer, and we wanted to make sure it was blue. And if we were to right click on this, we could simply bake this and it would create a new layer in our Rhino model. But what I wanted to highlight here is that we also have this ability, all of these pass-through components have the ability to hide or show parameters that are not being used, right? So you can see there are a number of inputs that I'm not really concerned with, whether it's visibility or the material or the line type. In this case, I just want a layer and the display color. So I can say hide unconnected parameters, and I get a sort of minified version of that component where it sort of hides all of the components that I wasn't necessarily using. I want to stop here and highlight the component on the right, which is the object attributes, the model object attributes component. And that's how we begin to assign different attributes to geometric objects. In this case, I have a sphere defined as a geometry, and I want to assign that sphere to be on a different layer, right? This new layer that I just created. Now, if I right click and click bake, it will bake the sphere into the Rhino viewport. And when I click on it, you can see in the layer panel, I have a new layer called geometry layer, but it's also then assigned that layer to the object, and the display color is using it by layer because I've defined that. So really, this model object attributes component opens up a lot of new possibilities. First, if we look closely, it lets you decide what geometry you want to assign the attributes to. We can set the name of that particular object. Each of these have layer attributes. So what layer do you want the object to be on? The visibility attributes can be defined. We have display attributes, and each of these inputs have their own attributes. We have drafting attributes like the print color and print width and line type. And so all of these things can now be explored and assigned to any of your geometry, which opens up a lot of new possibilities, which weren't previously available. Okay, so we've talked about that. We also wanted to add a bunch of new components that deal with annotations. Specifically, like I mentioned, we've had some rudimentary annotations available in Grasshopper, but now we have the full set that are available in Rhino, all exposed within Grasshopper. So you can create text entities, linear dimensions, radial dimensions, you name it. We also can create annotation styles or dimension styles. So all of the stuff that you can control within the Rhino annotation styles can now also be controlled in Grasshopper. And so you have the ability now to create these parametric models that are fully dimensioned, right? That can be used as more than just geometric objects. We're now creating and controlling annotations and to control how a drawing looks. Here, I'm scrolling through and changing the different annotation styles that are stored in the document. So I can quickly begin to look at how different annotation styles look as well. We also wanted to add a few components that deal with hatches as well as line types. And so I'll cover those in a little bit more detail. So hatches have been a little bit tricky to deal with in Grasshopper, but we have a number of new components that let you define not only hatch patterns, but how those hatch patterns get applied to a specific hatch, for example. And so here I've got a little 3D widget that I created, which is simply allowing 2 points to be moved within a space, which is controlling the color of the gradient that you're using. And then I'm also just then querying the document for different hatches that are available and quickly moving through to see which hatch looks the best on my object. And so there's a lot of new fine-grained control that you have over hatch objects in Rhino 8. If you've also been used Grasshopper, you may or may not have been frustrated by the line type visualization. It's very difficult to kind of create different types of line types for Grasshopper, but now we have the ability to not only create thicker lines, for example, but we can taper lines. using different sliders, or we can create dash lines on the fly. And all of this is parametrically controlled, this way you would control any different object. And so there's a lot of neat and interesting ways that you can start to explore and create different graphical styles now within Grasshopper. And what that lets you do is create things like this. This is a fully parametric Grasshopper model, which is completely driven within the Grasshopper preview. What I mean by that is you're not baking anything. You're not, everything you see here is being visualized directly through Grasshopper, including the shadows that you see. Those are the shadows or the hatches that you're seeing. Those are all done using the hatch objects and things like that. So now you can create really fully beautiful drawings or previews just using Grasshopper geometry or Grasshopper methods, and you have full control over that. Then, as I'll talk a little bit about baking, you then have the ability to start to bake those back into the Rhino document. All right, so lastly, or let's see, I got two more topics and then I'll try to wrap it up. We wanted to provide, there really has been no ability to control blocks from Rhino in a Grasshopper definition. And so now we have the ability to not only create block definitions, but then assign those block definitions to block instances, for example. So here I've just got some geometry. It doesn't matter what the geometry is, particularly in this case, but this is a panel system that I want to create a block for. So I have this new component on the far right that when I bake it, it adds a new block definition to our Rhino model. And if I then move or change that geometry and rebake the block definition, that same definition, it doesn't add a copy, it simply updates the existing block definition. Or let's say now I have 4 different block definitions for A, B, C, and D in my Rhino model, and I want to create a series of instances of those definitions. I can now do that directly through Grasshopper. So first I query the document to get all of the access to all of the 4 definitions that currently exist. And now I can create instances of those and really using a very simple algorithm, it can simply randomly generate these different block instances. And when I'm happy with it, the design, I can then bake those. And now each of those block definitions become block instances. So there's 23 different block instances in this particular design. So blocks have seen a lot of care and update. Lastly, I'll close with this new idea of baking. Grasshopper has really been limited in the past of its ability to bake. I've already shown the primary way that most users use it is to right-click on a component and select bake. And that's about the most you could do. Is you had a few attributes you could control. But what we decided to do was write a new bake component, which I think is really versatile and pretty powerful. It has a single input. That's all it does. It has a single input, which lets you pass in any content that I've just shown or any supported data type, right? So you can bake layers, you can bake annotation styles, you can bake line types, including geometry. And so let's take a look at a quick example. Let's say we wanted to bake a circle into our scene. We simply pass the circle in there, we click the update button, and now we have a circle that is available in our Rhino document. If I decide to move the slider, I can then manually click the update button and we have a new baked piece of geometry that is a smaller circle in this example. But there has this one instance where we can actually zoom in on the interface and click on the plus button, and that lets us add a second input, which now lets us control the baking using a Boolean input. Now, every time we move our slider, we have updated content, right? So every time the solution is calculated, we are also baking the content directly into our Rhino document. And I want to highlight that there's 2 different modes that this baker can operate in. The first mode is what we call insert mode. And insert mode is exactly how Rhino or Grasshopper currently bakes geometry into your definition, meaning every time you bake it, it adds a copy of that geometry into your definition. So here, if it's an insert mode and I move my slider, you can see that I get a copy at each step that I moved my slider added to the document. However, there's a second mode, which is called update. When update is involved, it's trying to keep track of the geometry that you're working on. So any change that you made, it's not making a copy, it's looking for that specific piece of geometry or that specific data type and only updating the attributes that have modified on that particular data type. And let's say we want to sort of bake an option into our scene, we can then release the content, meaning it's no longer being tracked. And now when we make our changes, it's now tracking the newly created object that we just created. So the baker is really powerful and I think has a lot of potential to really enhance your workflow as you're beginning to work through these things. So if you're interested, I would highly encourage you to check out the new Rhino 8 beta, which is publicly available. Like I said, if you have a Rhino 7 license, you can download Rhino 8 beta for free and check out the Rhino tab, which is where all of these new components live. And I don't know where I stand on time, but I think I'm about done and we can open it up to sort of Q&A.
Fantastic. Ooh. Thanks a lot, Andy. My mind is blown with the 2D drawing with the rendering directly from Grasshopper. That is just so cool. It was about time. All right, beautiful. So I'm going to open it up to questions from the audience. So the folks here on Zoom, is anyone, do you want to stop sharing perhaps, Andy?
Sure.
Anyone here on the room? You can just unmute yourself or raise a hand, however you feel. Before people warm up to a question, I don't know what I did. So, Andy, I've been following you for so many years, and specifically now after you've shown what you've been up to for the past decade, give or take, like you've worked on so many different projects, you've worked with so many different media, you've worked on hardware, you've worked on software, you've worked on plugins, you've worked on material, additive manufacturing, et cetera, et cetera. It's like, I'm very curious, how do you choose what motivates you? How do you find what at any given point, any given time, you want to spend your time on and your creative energy? Because it's very varied. It's like, it's not like.
Yeah, no, that's a good question. I don't know that I have a great answer. For me, I think I've had a lot of serendipity in being at the right place at the right time. And I know that's just, not a great answer, but I think I've been able to be I've been able to collaborate, find some really unique collaborators that have allowed me to, bounce ideas off of that have been sort of percolating in my head for a number of years. And then their impact has had or their influence has led me in different directions. And so first off, I'd say that I've had the opportunity to work with a number of great collaborators. And then secondly, I think like most people, I just try to stay curious. There's always a number of ideas that I feel like, are just something that I find interesting. And then for whatever reason, I can't let it go. I just sort of have to continue to try to unravel that thread a little bit. And sometimes it leads to nowhere. So there's a lot of projects that I didn't show, a lot of failures along the way, but those are how you learn too, right? So I think it's just a matter of staying open to different possibilities for me.
All right, wonderful. What do you think we can expect from Andy Payne in the next 2, 3, 5 years?
I wish I was a fortune teller. I can say that I'm incredibly happy being at Robert McNeil and Associates. I've been a big fan of theirs, and I think I started using Rhino way back in 2005. And so it's really been an amazing experience for me to be able to work with them. And I think that we obviously, as I said, we have some great collaborators. So being able to bounce ideas off of different colleagues, I think we have some real potential, some really interesting ideas that will begin to continue to develop in future iterations of Rhino. And so for me, and or Grasshopper. And if you haven't seen some of the other things that are available for Rhino, I would encourage you to look at, you know, the new feature list for Rhino 8, because it's quite long. There's a new feature list called Shrink Wrap, which actually uses a little bit of the voxel-based modeling now, but in Rhino, it's using a voxel representation to perform some of the shrink wrap operations. There's Grasshopper 2, which is led by David Rutten, who, you know, was the original creator of Grasshopper, and so it's a rewrite from scratch. It's really has some amazing new functionality that's also worth checking out. And so hopefully I get to work on some of those new projects as we move forward. And then for me, it's also about trying to manage family time as well, and trying to what you can expect is hopefully me still trying to prioritize time with my family.
Which is very important. I'm pretty much in that mindset also lately myself. So we have the chat here. We have the chat on YouTube. I may want to relay some questions to you. How would you advise? So Lucas Almasi is asking us, how would you advise beginners that are seeking more experience with Grasshopper?
It's a good question. I would advise them to just jump in. And I know that's frustrating. That's not a great answer. But what I mean is find a project that you can explore some idea, right? I tend to learn best by doing, right? By doing different things. And so I would encourage you, whether that's a studio project or a design project in an office, or even just a side research thing that you want to explore, begin, you know, just start figuring it out. And you're going to get stuck probably no matter what, but there's an incredible number of resources, most which are written by Jose, which teach you or try to help you navigate those pitfalls, right? And so there's a huge number of resources online, as well as in these schools, which let you then figure out how to navigate those problems and solve those problems. And for me, that's the most rewarding part of it, is that sort of aha moment when you have been stuck on this problem for days and you can't really figure it out, and then all of a sudden everything clicks and it works. And that's the sort of dopamine kick for me that I continue to seek, because and I can't stop doing it. It's sort of an addiction, unfortunately. But I would encourage you to, you know, just try to start with a project. It could be small. You can start small, but by doing it and fumbling through, you know, why doesn't it work this way, or how does the interface work, or just stumbling through how does it work, and how do I do the thing I'm trying to achieve, you begin to learn, and you just become more facile, and it becomes so much easier the second project, and then the third project, and then
I resonate 100% with that advice. Mengfei is asking us also, how much architecture design you share in total? How much architecture, I'm not sure if how much architecture design share in total Rhino and Grasshopper at this point? I'm not sure if the question is like, how much of the common code base is shared by the two platforms, or how much market share? Okay.
So you mean how much market share are there used by Grasshopper versus Rhino? I don't know that I have a firm answer on that. I do feel like it was discussed internally at one point over the last couple of months, and I was shocked to find out that Grasshopper users, I think, only made up somewhere between 10 and 20% of the total user base, which was shocking to me because I figured it would be much higher than that. But all that means to say is that there's more opportunities for people to jump in. And I find Grasshopper incredibly fulfilling, because for me, it opened up the possibility to do all these things that I wanted to do in Rhino, which would take a long time to have to model and things like that. Now I can create a parametric model and explore these options that are very quickly, right? And so I would highly encourage you to jump in with Grasshopper, but even with Rhino, just starting with Rhino, among the Rhino users, how much? Oh, okay. I don't have an answer for that one. I don't know how many are architects versus industrial designers. You know, Rhino is a really interesting project in that it's really a three-dimensional geometry engine. I think a lot of applications out there really tailor their user experience to a specific industry, right? Revit is really, and AutoCAD are really specifically towards architecture or engineering. There's a number of jewelry designers that use their own applications, or product designers might use one software. Rhino is really agnostic in that way, and that it's really about geometry, and it's really good at geometry. And so we have a really large user base. I think we started as a plugin for shipbuilders, which needed some complex geometry form making tools. And so we have a number of users that are still using it for shipbuilding, jewelry design, industrial design, to architecture and engineering, and anywhere in between. And so I think that's something that makes it unique, but also a bit of a challenge to be able to still be relevant in all of those different domains.
It's so funny that you say that it's only like 15 or 20% of Grasshopper, because I literally learned Rhino just because I wanted to use Grasshopper.
I was the same way.
That was my personal case. I would have never thought of that. If you have a couple, I know we are over the hour, but if you have a couple of minutes, the YouTube chat is like booming. There's like so much love and so many emojis. Please check it out afterwards. Chris is asking whether if any of the updates that you have presented today were coordinated with the Elephant team.
That's a great question. A lot of the functionality that I showed does kind of replicate similar functionality with the Elephant plugin. Unfortunately, we didn't have a lot of back and forth when we were developing it. So that's why you do see some of the overlap. I will say that, there were a number of plugins, not just Elephant. There was Andrew Human's plugin also had some functionality which allowed you to control attributes. Elephant, there's a number of them, and they all filled a different sort of gap that was missing. And I hate that it took us this long to sort of address that gap, but the hope is that now that we can create a sort of native set of components that really handle and encapsulate these Rhino objects, that people can start to rely directly on those native types, and not to, we definitely don't want to discourage third-party plugin development. In fact, it was a very necessary plugin for many people for many years. And there's probably still a lot of functionality that it does that these new components still can't do. So we're always trying to encourage third-party development and those people who want to get into coding and develop their own ideas. We definitely don't want to discourage that, but we just felt like it was time internally to start to develop a sort of these gaps, to fill some of these gaps that we didn't have natively.
Mm-hmm. Mali Tribune is asking now, with so much attention that there is going on generative AI these days, where do you see parametric design fitting in the landscape of all these new public technologies that are available and accessible to the community?
Yeah, there's a whole conference, I'm sure, with a number of speakers that are trying to address that. But I guess I have a follow-up question then to that is, do you mean specifically from a Rhino and McNeil standpoint, or me just generally speaking? Because McNeil, and I think anybody internally would probably agree with this statement, is that we are not at the bleeding edge necessarily of newest technology, right? So I think we like to keep our eyes on what's happening and see who's doing what and how they're doing it. But we also kind of want to watch, how some of these trends are progressing. We're not big enough to really vigorously attack something, and if it doesn't work out, then we're sort of lost from a business perspective, right? So we kind of sit back and watch. But then once things start to gel, and one of the things I wanted to mention is that we do try to create Rhino and Grasshopper in such a way that we really open third-party development. So people who want to explore ChatGPT for Grasshopper, or mid-journey and feed that information, or stable diffusion and feed that information directly into Grasshopper or Rhino, you certainly have the ability to make your own plugins and develop that. And that's the sort of things that we start to look for, right? What are people starting to do? What are the trends? And once it becomes a little bit more mature and we decide that's sort of the direction we want to take the product, that's where we sort of start to drive things. So it will probably, from a McNeil standpoint, I would probably say that it might take a little while for us to kind of to see how that starts to play out. From a personal standpoint, I think it'll have a pretty large impact, at least on the day-to-day stuff. I think there's a lot of opportunities for ideation and even just marketing, copy, and you name it. There's so many applications that it can be applied to, and I think it's a great way to start to augment your own design process. That said, I think there's still a lot of questions, over authorship and intellectual property and things that really, from a technical and legal perspective, are sort of in this gray zone. And so I still think it will have a really big impact on the industry as a whole, but I think it'll be really interesting to see, how we navigate that as an industry and as a country, really, to see how these things start to play out.
Mm-hmm. Wonderful. Sunny is asking, can we expect animation tools to be integrated into your system?
Yeah, yes and no. I mean, we certainly keep an open mind, and we really rely on user feedback as to stuff we need to develop. In fact, if you haven't been on the discourse forum for Rhino, the Rhino 3D discourse forum, highly encourage you to get online. And if there's something you don't agree with, or you want to complain about, or tell us there's a feature that is missing, that's how we determine what to focus on. And our developers are on that, waiting to answer questions, every day. And so we don't really have an intermediary between, I've worked at a number of different companies, and there's a lot of hierarchy, and there's really a disconnect sometimes from software developers and the customer. We like to have a really direct line directly to the customer. And so when things aren't working, or if people want a certain feature, if they yell loud enough and stand up on their table, that's when we know this is something we really need to address. And so I would say animation tools are certainly something we might veer towards. I will say there's probably a large project that myself and I should have mentioned, I forgot to mention this, that all of the Grasshopper features that you were just looking at, the new data type stuff was really done by myself and a fellow colleague named Kike. And Kike and I have also been talking about a project to continue essentially an entirely new rendering pipeline through Grasshopper for material creation, shader creation, that sort of thing. It's an incredibly large project, as you can imagine. And so there's no telling as to where that might lead, or even really the shape of what it might lead. But I know we're both interested, once Rhino 8 ships and is delivered to the public, that we finish off some of the remaining items that we need to take care of. We'd like to shift gears and start to look at that as a topic. So I could see that as a development of materials developing sort of into the idea of adding some animation tools.
That's awesome. If you need help. And I think this is going to be the last question, because we don't want to take over your entire evening. But Roberto Arguelles is asking, what would be your recommendation to start getting involved in robotics in architecture without having direct access to robotics or to robot equipment to start with?
Yeah, no, that's a great question. It sort of boils down to the same thing that we struggled with Monolith, in that we started by tailoring it towards multi-material 3D printers. And for many people, those machines are just out of reach, right? They're incredibly expensive machines, and it limited our user base quite a bit, I think. And also, so I can see a corollary to the stuff we found out with robotic fabrication. Probably the easiest way I think, and Jose, you can correct me, maybe, would be either to look at some sort of partnerships with schools, or really looking at different conferences, right? There's a number of conferences which offer workshops They might be a couple-day workshop or a week-long workshop, which still are not inexpensive, but you're also not buying an entire machine. But it lets you at least get access to a machine and learn how to program them correctly and really learn the workflows and a little bit of the domain expertise. From that, you could then start to parlay that into maybe job opportunities that explore robotic fabrication, right? So even if it wasn't necessarily in the architecture industry, robotics are used a ton in automotive manufacturing and you name it. And so you could start to explore opportunities that way as well.
Absolutely.
Yeah.
If I may add to that, we also tend to have this narrow vision of robotics in architecture, meaning a 6-axis robotic arm that is somehow fabricating objects. And we tend to forget that robotics is like a very ample concept. So a Roomba that is vacuuming your apartment, that is a robots in architecture, you know, or a system where you have sensors and you activate lights, etc., and the house is smart and knowledgeable about where you are and what you're doing in response to that. That is literally turning your apartment into a robot. So
that's a great idea. That's a great point.
And you worked on this on your thesis, on these like devices that were like sensing you, and they were like trying to give you comfort in real time, thermal comfort, etc. So
yeah,
robots is a very, very wide field that you can take in many different aspects, you know.
That's a great point. And you could even find, you know, deconstructing toys, right? Toys are a really good way to find some actually fairly sophisticated motors and sensor technologies and deconstructing them and then reappropriating them. Or, as I said, even getting started with Firefly and things like that, where you're just getting started with low-cost microcontrollers and learning how those work, and then building your own sort of custom robotic kit that you designed yourself. And so that's also a good avenue to start to explore.
Fantastic. Andy, we don't want to take any more. We are really, really thankful to you for being here tonight. I'm going to do a round of virtual. Everyone is joining me on this. Thank you so much. It was a pleasure to see you again.
Thank you. Thank you for inviting me.
And I hope to run into you soon, sometime in the physical world. It's been forever.
Absolutely. Me too. It has been too long.
I know. Thanks a lot, Andy. Have a good evening. And thanks everyone.
Bye-bye.
Bye-bye.